Atoms, the fundamental building blocks of matter, are incredibly small. Each element on the periodic table is defined by its unique atoms. A crucial characteristic of an atom is its atomic weight, which represents the average mass of an atom of an element. This value is expressed in atomic mass units, or AMU, where 1 AMU is equal to 1/12 the mass of a carbon-12 atom. Atomic weight is not a whole number for most elements. This is because it takes into account the existence of isotopes. Isotopes are atoms of the same element that have the same number of protons, but different numbers of neutrons. As a result, isotopes have the same atomic number, but different mass numbers. For example, carbon has 2 stable isotopes, carbon-12 and carbon-14. Both isotopes have 6 protons, but carbon-12 has 6 neutrons, while carbon-14 has 8. To calculate atomic weight, we take the weighted average of the masses of all naturally occurring isotopes of an element. The contribution of each isotope to the average is determined by its natural abundance. More abundant isotopes have a greater influence on the atomic weight. This is similar to calculating the average age of students in a classroom, where the age of each student is weighted by the number of students of that age. Let's delve deeper into how isotopes influence atomic weight. Take chlorine as an example. Chlorine has 2 main isotopes, chlorine-35 and chlorine-37, with natural abundances of approximately 75% and 25% respectively. This means that for every 100 chlorine atoms found in nature, approximately 75 will be chlorine-35 and 25 will be chlorine-37. To calculate the atomic weight of chlorine, we multiply the mass of each isotope by its natural abundance and sum the results. For chlorine, the atomic weight is calculated as follows: 0.75 times 35 AMU plus 0.25 times 37 AMU is approximately 35.5 AMU. This weighted average reflects the relative proportions of chlorine-35 and chlorine-37 found in nature. The concept of weighted average is crucial in understanding atomic weight because it explains why the atomic weights of most elements are not whole numbers. The presence of isotopes with different masses results in a fractional atomic weight that reflects the average mass of an element's atoms. This understanding is fundamental in various chemical calculations and analyses. Chemists often work with a large number of atoms or molecules. To simplify calculations, they use a unit called the mole. A mole is defined as the amount of substance that contains the same number of entities, such as atoms, molecules, ions, etc., as there are atoms in 12 grams of pure carbon-12. This number of entities is known as Avogadro's number, which is approximately 6.022 times 10 to the 23rd. Avogadro's number is an incredibly large number, almost beyond human comprehension. To put it into perspective, 1 mole of grains of rice would cover the entire surface of the Earth to a depth of over 75 meters. This constant allows chemists to relate the microscopic world of atoms and molecules to the macroscopic world of grams and liters. The relationship between moles and Avogadro's number is analogous to the relationship between dozens and the number 12. Just as a dozen always contains 12 items, a mole always contains 6.022 times 10 to the 23rd entities. This concept is essential for understanding the mole-mass-particle relationships that are fundamental to chemical calculations. The mole, Avogadro's number, and molar mass are interconnected concepts that are crucial for understanding the quantitative aspects of chemistry. The molar mass of a substance is the mass of 1 mole of that substance, expressed in grams per mole, or g-mole. The molar mass of an element is numerically equal to its atomic weight. For example, the atomic weight of carbon is 12.011 AMU, so the molar mass of carbon is 12.011 g-mol. This means that 1 mole of carbon atoms has a mass of 12.011 grams. Similarly, the molar mass of water, H2O, is 18.015 g-mol, which means that 1 mole of water molecules has a mass of 18.015 grams. The relationship between moles, mass, and particles can be summarized as follows. 1 mole of a substance contains Avogadro's number of particles and has a mass equal to its molar mass. This relationship allows chemists to convert between mass, moles, and the number of particles of a substance, which is essential for various chemical calculations, including stoichiometry, solution concentration, and gas laws. The terms atomic mass and mass number are often used interchangeably, which can lead to confusion. However, it's essential to distinguish between these two terms. The atomic mass of an atom is the average mass of all the isotopes of that element, taking into account their natural abundance. It is expressed in atomic mass units, or AMU. On the other hand, the mass number of an atom is the total number of protons and neutrons in the nucleus of an atom. It is a whole number, and does not consider the relative abundance of isotopes. For example, the mass number of carbon-12 is 12. That's 6 protons plus 6 neutrons, while the mass number of carbon-14 is 14, 6 protons plus 8 neutrons. The key difference between atomic mass and mass number is that atomic mass is a weighted average that reflects the isotopic composition of an element, while mass number is a simple count of protons and neutrons in a specific isotope. Atomic mass is used in most chemical calculations, while mass number is primarily used to distinguish between isotopes of an element. Understanding molar mass is crucial in various scientific and everyday applications. In chemistry, molar mass is used to convert between mass and moles, which is essential for stoichiometry, the study of quantitative relationships in chemical reactions. By knowing the balanced chemical equation and the molar masses of the reactants and products, chemists can calculate the amount of reactants needed or products formed in a chemical reaction. Molar mass is also pivotal in determining the concentration of solutions. Molarity, a commonly used unit of concentration, is defined as the number of moles of solute per liter of solution. By knowing the mass of the solute and its molar mass, chemists can prepare solutions of desired concentrations. Beyond chemistry, molar mass has applications in various fields such as medicine, environmental science, and materials science. For instance, in medicine, molar mass is used to calculate dosages of medications, ensuring that patients receive the correct amount of active ingredients. Stoichiometry relies heavily on the concept of molar mass. Consider the reaction between hydrogen gas, H2, and oxygen gas, O2, to form water, H2O, 2H2 plus O2, 2H2O. This balanced equation tells us that 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. However, in practical laboratory settings, we work with grams of substances, not individual molecules. This is where molar mass comes into play. The molar mass of hydrogen gas is approximately 2 grams per mole, and the molar mass of oxygen gas is approximately 32 grams per mole. Using these molar masses, we can convert the coefficients in the balanced equation into mass ratios. For example, the equation tells us that 2 moles of hydrogen react with 1 mole of oxygen. Using molar masses, we can determine that 4 grams of hydrogen, 2 moles times 2 grams per mole, react with 32 grams of oxygen, 1 mole times 32 grams per mole, to produce 36 grams of water, 2 moles times 18 grams per mole. This demonstrates how molar mass enables us to translate the microscopic world of molecules and balanced equations into the macroscopic world of measurable masses in the laboratory. The concept of molar mass might seem abstract, but it has tangible implications in our daily lives. For instance, baking involves chemical reactions, and molar mass plays a role in determining the quantities of ingredients needed. Baking powder, a common leavening agent, typically contains sodium bicarbonate, NaHCO3. The amount of baking powder needed to produce a certain amount of carbon dioxide gas, CO2, for leavening depends on the molar mass of sodium bicarbonate. In medicine, molar mass is crucial for calculating dosages. Medications often contain active ingredients in very small amounts. Molar mass allows pharmacists and doctors to determine the precise mass of a drug needed to deliver a specific dose of the active ingredient. This ensures that patients receive the correct amount of medication to be effective without causing adverse effects. These examples highlight how molar mass, though often operating behind the scenes, plays a vital role in ensuring accuracy and consistency in various aspects of our lives, from the food we eat to the medications we take. Molar mass is a fundamental concept in chemistry that connects the microscopic world of atoms and molecules to the macroscopic world of grams and liters. It allows chemists to quantify chemical reactions, determine the concentration of solutions, and understand the properties of substances. The ability to convert between mass, moles, and particles is essential for various chemical calculations and analyses. Understanding molar mass is not limited to chemists in laboratories. It has practical implications in various fields, including medicine, environmental science, and materials science. From calculating dosages of medications to determining the composition of alloys, molar mass plays a vital role in ensuring accuracy and consistency in countless applications. By grasping the concept of molar mass, we gain a deeper appreciation for the quantitative nature of chemistry and its impact on our daily lives. It is a testament to the power of chemistry to explain the world around us and to develop solutions to challenges in various fields.